There's a kind of damage that arrives not through ignorance, but through a name. A name can encode a verdict before the trial begins, install a suspicion so early in a student's encounter with an idea that the idea never quite recovers. Mathematics has suffered this, methodically and for centuries, through a word chosen not to describe but to dismiss. That word is imaginary. And its consequences have compounded quietly through every generation of students who arrived at the square root of -1 and were told, by the name itself, that they were about to do something false. A history of evasion. The trouble began with a question that polynomial algebra could not ignore. In the 16th century, Italian mathematicians were competing, sometimes ferociously, sometimes in public contests, over methods for solving cubic equations. Scipione del Ferro, Niccolò Tartaglia, and Girolamo Cardano each played a part in developing what is now called Cardano's formula, a general method for finding roots of cubics of the form x cubed plus px equals q. X equals the cube root of q over 2, plus the square root of the fraction with numerator q squared and denominator 4, plus the fraction with numerator p cubed and denominator 27, plus the cube root of q over 2 minus the square root of the fraction with numerator q squared and denominator 4, plus the fraction with numerator p cubed and denominator 27. The formula worked, but it had a structural embarrassment. Certain cubics that were known to have 3 perfectly real, perfectly respectable solutions produced intermediate steps involving the square root of a negative number. The mathematics was producing an answer you could verify via a route that seemed to pass through impossible territory. The case that forced the issue was the cubic x cubed equals 15x plus 4. The solution is obviously x equals 4. You can check it by hand. But applying Cardano's formula to this equation yields x equals the cube root of 2 plus the square root of -121 plus the cube root of 2 minus the square root of -121. This is the square root of -121 equals 11. The square root of -1 sitting in the middle of a calculation whose output is a real integer. Cardano himself called such quantities sophistic and largely refused to engage with them. The temptation and the widespread response was to treat these expressions as a formal nuisance, a step in the working to be tolerated and then discarded once the real answer appeared. Raphael Bombelli refused that evasion. In his L'Algebra of 1572, he confronted the problem directly. He reasoned that if the cube root of 2 plus 11, the square root of -1 equals a plus b, the square root of -1 for some real a and b, then cubing both sides and matching real and imaginary parts gives a cubed minus 3ab squared equals 2 empty, and empty 3a squared b minus b cubed equals 11. Guessing a equals 2, b equals 1. Both equations hold. Therefore, the cube root of 2 plus 11, the square root of -1, equals 2 plus the square root of -1. And by symmetry, the cube root of 2 minus 11, the square root of -1, equals 2 minus the square root of -1, giving x equals open paren 2 plus the square root of -1, close paren plus open paren 2, minus the square root of -1, close paren, equals 4. The impossibility cancels. The real answer emerges. Bombelli's contribution was not to explain what the square root of -1 was. He called it with a kind of pragmatic honesty, più di meno, more than minus, but to demonstrate that it could be manipulated coherently, that it obeyed rules, and that taking it seriously rather than dismissing it was the only way to make the arithmetic work. This was mathematics using a concept it did not yet understand and arriving at correct answers. The appropriate response was curiosity. What arrived instead, 65 years later, was Descartes. Descartes names the verdict. In La Géométrie of 1637, René Descartes coined the term imaginaire. His intent was not to celebrate these numbers or to acknowledge their utility. Bombelli had already demonstrated that, but to quarantine them. For Descartes, numbers were ultimately grounded in geometric lengths and magnitudes. A quantity that could not correspond to a spatial measurement was not, in any serious sense, a quantity at all. The term was a philosophical ruling disguised as a label. It stuck, and it stuck in the worst possible way, not as specialist jargon that students learned to see through, but as the name students encounter first before they know enough to question it. Imaginary encodes the verdict that these numbers are not real, in the colloquial, not just the mathematical sense, before any instruction has begun. The student who arrives at the square root of -1 carrying the word imaginary has already been told the conclusion. Leonhard Euler worked with these numbers without apology. He introduced the notation I for the square root of -1 around 1777 and deployed it throughout his work in analysis. His formula, e raised to the I theta power equals cosine theta plus I sine theta, demonstrated that the exponential function, the trigonometric functions, and the lateral unit are all aspects of a single structure. At theta equals pi, this gives what is now called Euler's identity, e raised to the I pi power plus 1 equals 0. Euler used this machinery because it worked, because it unified disparate areas of mathematics and produced results that could be independently verified. He was not troubled by the name. The name for him was not the mathematics, but Euler was Euler. The name troubled everyone else. What Gauss understood, Carl Friedrich Gauss had no patience for the confusion, and unusually, understood its source precisely. In an 1831 paper on the metaphysics of complex numbers, he noted that the term imaginary quantity was rooted in a false conception and had caused precisely the damage you would predict from naming a mathematical object after its supposed non-existence. He proposed instead that +1, -1, and the square root of -1 be called direct, inverse, and lateral units respectively. Lateral is geometrically exact in a way that imaginary never was. The complex plane has two axes, real and lateral, and I marks the unit step along the lateral axis. Multiplying any number by I performs a rotation of 90 degrees counterclockwise in that plane. The operation has a precise geometric meaning. Z times I equals R e raised to the I theta power times e raised to the I pi divided by 2 power equals R e raised to the I times open paren theta plus pi divided by 2 close paren power tor. The magnitude is preserved. The angle increases by pi over 2. That is all that happens. There is nothing impossible about it. There is nothing that requires qualification or apology. Lateral describes what the unit does. Imaginary describes what Descartes thought of it. Gauss lost the nomenclature battle. The word had 2 centuries of institutional momentum behind it by the time he objected, and imaginary has remained the standard term in every textbook since. But his diagnosis was correct, and the argument for rehabilitation is not nostalgic, it is structural. The damage is still being paid, in every classroom, year after year. The polar question, a separate but related problem, concerns how the arithmetic is framed. Complex numbers have 2 natural representations. The first is rectangular or Cartesian, z equals a plus bi, where a is the real component and b the lateral component. The second is polar. Z equals r e raised to the I theta power equals r times open paren cosine theta plus I sine theta close paren, where r equals the absolute value of z equals the square root of a squared plus b squared is the modulus, and theta equals arg z is the argument, the angle, the number makes with the positive real axis. Multiplication is where polar form reveals its character. Given 2 complex numbers, z sub 1 equals r sub 1 e raised to the I theta sub 1 power, and z sub 2 equals r sub 2 e raised to the I theta sub 2 power. Z sub 1 times z sub 2 equals r sub 1 r sub 2 times e raised to the I times open paren theta sub 1 plus theta sub 2 close paren power. Multiply the magnitudes. Add the angles. The algebra is 2 operations on 2 numbers. What this exposes is that multiplication is fundamentally geometric. It is rotation and scaling in the plane, not iteration of addition along a line. The claim that multiplication is repeated addition is a description of a special case, non-negative integers along a single axis, that the curriculum has somehow elevated into a definition. The instinct to teach polar form earlier, perhaps as the primary frame, is therefore sound. But there is a structural difficulty. Addition is not clean in polar coordinates. To add z sub 1 and z sub 2 expressed as magnitude-angle pairs, you must convert to rectangular, add component-wise, and convert back. For the operations children encounter first and rehearse most heavily in primary education, rectangular is the natural frame. The stronger proposal is not polar primary wholesale. It is this. Teach multiplication as rotation and scaling from the beginning, while retaining rectangular form for addition. Introduce the duality as two languages for the same object, each better suited to certain operations, rather than presenting them as separate topics that happen to share notation. What changes if you do this? The payoff is not local. Reframing multiplication at the root reshapes the entire downstream curriculum because the downstream curriculum is mostly one idea expressed at different levels of zoom. Negative numbers stop being philosophically strange. Under the current framing, -1 sits to the left of 0 on a number line, pointing in the wrong direction, governed by a rule. Two negatives make a positive, that students memorize without understanding. The rule is not wrong, it is just missing its reason. Teach multiplication as rotation, and the reason is immediate. -1 is a rotation by pi radians. Multiplying by -1 twice is 2 half turns, which returns you to the start. The rule is not an axiom, it is a geometric consequence. -1 times -1 equals e raised to the I pi power times e raised to the I pi power equals e raised to the I times 2 pi power equals 1. The number line announces its own incompleteness. A line is one-dimensional. The moment multiplication is understood as rotation, a line is an insufficient stage. You need a plane to rotate in. The student who internalizes this early does not experience 2D numbers as a strange extension grafted onto the real line in secondary school. They experience them as the natural habitat of an operation they already know. The lateral unit becomes a discovery, not an imposition. If -1 equals e raised to the I pi power corresponds to a rotation of pi, and 1 equals e raised to the I times 0 power corresponds to a rotation of 0, then the question presents itself without any prompt. What corresponds to a rotation of pi over 2? The answer is e raised to the I pi divided by 2 power equals I. The student has not been handed a new piece of mathematical machinery alongside an apology. They have followed a logical consequence to its natural end. The lateral unit is the answer to a question the curriculum itself raised. Euler's identity loses its air of miracle. E raised to the I pi power plus 1 equals 0 is routinely presented as one of mathematics' great coincidences, 5 constants in one equation. It is neither coincidental nor miraculous. It is what happens when a rotation by pi radians is expressed in the language of the exponential function. Students who arrive at it through this route do not experience revelation. They experience recognition. These are not 4 separate insights. They are one insight at 4 different levels of resolution. The fragmentation that makes the mathematics curriculum feel like a sequence of unrelated shocks is a teaching artifact. It is not inherent to the mathematics. The unit in nature, there is a harder argument still, that the lateral unit is not merely useful in physics, but structurally necessary, that the universe, at its most fundamental level, does not run on real numbers. The time-dependent Schrödinger equation, which governs the evolution of quantum systems, is IH bar the fraction with numerator partial differential psi and denominator partial differential t equals negative. The fraction with numerator h bar squared and denominator 2m nabla squared psi plus v psi, or in the compact Hamiltonian form. IH bar the fraction with numerator partial differential psi and denominator partial differential t equals h hat of psi. The I on the left-hand side is not a notational convenience. It is load-bearing. The wave function psi is complex-valued. It takes values in the complex numbers, not the real numbers, and the I in the equation is what makes its time evolution rotational in the complex plane rather than exponential along the real line. Without it, the wave function would not oscillate, it would grow or decay, and the probability interpretation, where the absolute value of psi squared gives the probability density, and must therefore integrate to 1 and remain normalized over time, would collapse immediately. Interference, the phenomenon that distinguishes quantum mechanics most sharply from classical probability, requires complex amplitudes precisely because it requires phases. Two probability amplitudes psi sub 1 and psi sub 2 interfere as the absolute value of psi sub 1 plus psi sub 2 squared equals the absolute value of psi sub 1 squared plus the absolute value of psi sub 2 squared plus 2. The real of open paren psi sub 1 psi sub 2 horizontal bar close paren. The cross term 2, the real of open paren, psi sub 1, psi sub 2, horizontal bar, close paren, is the interference term. It depends on the relative phase between the two amplitudes. Information that exists in complex numbers and has no analog in real ones. Remove the complex structure and interference vanishes. Remove interference and you no longer have quantum mechanics. This is not an abstract point. In 2021, a paper in Nature by Chen et al. Reported experiments demonstrating, via a three-particle entanglement inequality, that any formulation of quantum mechanics over real numbers cannot reproduce the full set of quantum correlations. The complex number structure of quantum theory is not a convenient mathematical choice. It is a constraint imposed by nature. The student taught to regard I as imaginary, as a sophistic convenience, a computational ghost that cancels out before the real answer appears, is being prepared badly for physics. In quantum mechanics, the lateral unit does not cancel out. It is part of the answer. The tragedy of the upstream fix. The problem with this entire proposal is that the fix is upstream of where specialists operate. The change required is not in how complex analysis is taught at university, or even how complex numbers are introduced in secondary school. It is in how multiplication is introduced to 7-year-olds. It requires revising the most foundational concept in arithmetic, at the earliest stage of formal education, in institutions governed by curriculum bodies that move on timescales measured in decades. The people most qualified to advocate for it, mathematicians, physicists, engineers who use complex numbers daily, are the people who have already cleared the hurdles and typically cannot remember what made them hard. Competence erases the memory of difficulty faster than pedagogy corrects for it. So the word imaginary persists. The rotation stays hidden. The shocking revelations are scheduled one per syllabus year. Negative numbers in 1 year, complex numbers years later, Euler's identity as an optional curiosity, quantum mechanics as a final year surprise in the order that history, not logic, dictates. None of this is inevitable. The name was chosen poorly and early. It could be chosen better. The framing of multiplication was fixed at a special case. It could be fixed at the general one. The duality of rectangular and polar could be introduced as a feature rather than deferred as an advanced topic. Lateral numbers could arrive in the curriculum as the answer to a question students have already asked, rather than as the beginning of a defensive explanation. These are choices. They were made once, they were never revisited, and they are now transmitted as if they were the shape of the subject itself. They are not. They are the shape of a historical moment that has outlasted its justification by 4 centuries.